Okay, I'm supposed to do a good job today because Blas is not here and he's depending on the recordings. Blas is not here and he's depending on the recordings, so I'm supposed to do a good job today.
Hi, Blas.
I should have actually not told him that, and that we should have pranked him. Done pre-calculus instead.
Did he specifically tell you to do a good job?
Yes. Yes. He was really anxious because he has parent-teacher conferences tonight.
You don't always do a good job.
There you go. So I'm not assigning any homework other than things that might appear on the exam. I'm trying to keep it light. I think I talked to Dr. Przinski this last week, and he had told me, I was here when they actually had changed abstract algebra from a 2-semester course to a 1-semester course. And I had not thought about this, maybe I was too young at the time, but the content for the comps has not changed. So the content for the comps is over a 2-course spread, and now it's over a 1-course spread. So I asked him about that. And then I also talked to an abstract algebraist at Manhattan College this weekend, and he had said, that's a lot for 1 semester. He assumed it was 2 semesters. I'll do some talking around and find out if there's a way that we can cut back some of the content, at least for the fall that's coming on the comps, so that you can focus more on the stuff that we did in the beginning. And I'll get back to you on that. So if you're feeling like it's a lot of stuff coming at you at once, it is. Not my fault. I was too young to speak up. So 68 and 90 has computational problems that I think you're gonna find them not difficult. That's my guess. So today what I'm going to do is finish up ideals, and my plan is to just stop with splitting fields, which is the one more topic, and that's it. And so that we'll just review, and I'll show you how to do more proofs. And then the take-home final, I'll try to gather together some ideas so that you're doing something that's comprehensive, yet it's doable and not as taxing as some of the other things we've done here. So like I didn't give you a checkability theorem for rings, subrings, but there is one in your book. Has something to do with A minus B, so you can dig it up in Fraley. It's a nice checkability theorem. I call them checkability theorems because they're what physicists called show me proofs. Show me something's right. You just check. So if you have a ring and a subset, that subset's going to be an ideal if and only if, number one, the I is non-empty. A minus B is an I for all A and B and I. So it's something like closure under subtraction. That takes care of inverses and worrying about additive inverses. And then you have the important piece, number 3, that says that RA has to be an I and AR has to be an I for all R and A and all A and I. Lots of letters. And you would use this because directly proving sometimes something is an ideal, it can be challenging. So you'd go through and just check off each one of these things. And you're going to see I use this in a proof later on, this version of the ideal theorems, because I want to use it for something. It turns out that I actually need to use something from this list. So if I always have to be given a ring first. So given a ring Z is I equals 0 an ideal. Well, is that one true? A minus B belongs to I for all A and B and I? Yep, that's true. So I got that one checked off. What about this one, that RA is an I and AR is an I for all? Well, that's true, because 0 times anything is 0, and so we get the second piece is true. What if I have just a commutative ring, and I fix one element, A, from the ring, and I form a set where I is R times A, such that R belongs to capital R. Too many R's. So A is fixed. So think of a ring like Z5. I take my A to be 4. It's one element, and I just form all the elements R times 4. Well, we go through the checkability theorem. Notice here I didn't use A's and B's here because I have an A in the set, so don't reuse that A. So I'm going to rewrite the checkability theorem with X's and Y's. It's just good practice to do. So I check off the first one. So I take an X and a Y in the ideal, and well, it's not ideal yet. Hopefully it will be. and I take x equals RA and y equals SA, because if they're in that set I, that's what they have to look like. X minus y becomes R times A minus S times A, which by the ring properties distributive law, I can take the A out to the right, your right, my left. And it's of the form T times A, where T is an element in R, so that tells me that X minus Y belongs to R. So I got the first property. So again, the second checkability condition, I used an X instead of an A because I already have an A that I fixed from the ring and I don't want to reuse that again. So does it satisfy this? Well, if I take an arbitrary Y belonging to the ideal, which I don't know is an ideal yet, but I'm calling it so, Y equals S times A. That's the way it has to look like if it belongs to the set I. And then if I take an arbitrary R in the ring, then R times X is R times S times A, which I can rotate everything around by commutativity. And I've written it now in the form of T times A. So I have that R times X is inside the ring. And X times R is also in the ring too. It's not that difficult to go the other direction. So I have the second condition as well. Good? These are straightforward proofs. I think I want to put things like a couple things like this, where you're just straightforward going through and checking things to see if they do or don't. And Fraley has examples of things that are not ideals and are ideals. He has, right after he gives you a definition, he has a few examples right after that. So if you go to the book, you'll find more examples of ideals and non-ideals. Questions so far?
You went so fast I didn't get it. Whether which subring are we proving to be an ideal?
In this case, the subring would be this. So R is an arbitrary commutative ring. The only condition I have is it is a commutative ring. I can always form the set. So I fix an A and R, an arbitrary A and R. So if you want a specific example, I don't have my marker.
So it's similar to if you start with Z, then if I do NZ, then this is sort of the same idea. What is RA?
No, so let's take something smaller. Take Z5, okay? So that's my R, commutative ring, correct?
Yes.
Then I take A to be an arbitrary element in that ring. Well, I take it to be 4.
Okay.
Then I will be the set of R times 4 such that R belongs to Z5. So you can actually write down what this is because Z5 is 0, 1, 2, 3, 4. So what do I get from this? I get 0, 4, 3, and then
12, 2.
I'll trust you guys.
And
We got one more?
and one.
One. So I get all of Z5 back, right?
Okay.
So
Sometimes you will, sometimes you won't.
yeah, it doesn't mean that I will get the whole thing back, right? So that's what that is for the specific example.
Okay.
And the previous one was a very trivial one. Make sense?
Does an ideal have to be an additive group?
Yes, it does because it's a subring. So the first condition of an ideal is it's a subring.
So in that case, how is 4, the element 4, be a additive subgroup? Unless it was
It's
this
the element
way.
4 by itself is not. In this particular example, I fixed an element in the original ring
Created an ideal out of it.
out of it. Yes.
Got it, okay. Understood.
And the additive group is a huge thing because it takes you very far because you know so many things about additive groups.
And could you stop for a
Sure.
second? The first thing you're trying to prove that X minus Y belongs to I,
Mm-hmm.
and your conclusion was X minus Y belongs to R.
Well, no. The conclusion was if I take X minus Y, I can write it as a form of one of the elements in the I. To be an I, it has to be a multiple of A. Right? It is a multiple of A. So
Your conclusion there.
yeah, so this belongs to I, T, where T belongs to R.
With
Yeah, that should be on.
Therefore, X minus Y belongs to
the
I.
implies.
The last, where I get confused because the last line.
Oh, this should be
says-
I, yes,
Yeah.
this should be I, correct.
Okay.
Sorry, Blas, that should be I. Okay, Any other questions? So, I seems like a brand new definition. It's not actually. It's the abstraction of a coset. This is like a coset. And you're going to see as we move forward, it's almost like you have to see the end game first. Then you'll realize it's a coset. It's the ring version of a coset. That's where we're headed.